It's quite an honor to be here as the Lytle Lecturer. The previous lecturers are all people that I know well, and it's humbling to be included in their company as, with this honor, and that means a lot to me. Now, as the three titles of my talk might suggest, putting this talk together was something that involved a fair amount of introspection. And this talk may seem a little bit like Forrest Gump telling his life story while sitting in a bench waiting for a bus. It's fair to ask, is that self-indulgent? Well, yeah, but I hope that you find some things of interest or at least entertaining in what I have to say. Also, given the time constraint and my faulty memory, I'm sure I've left out many kindnesses, places, and forks, so apologies are in order. Except I'm not sure if it's those I've admitted or those I've included. So now we'll get the start of my, my journey here. By the way, I'll let you figure out the acronyms here. And this starts in my home state of New Jersey, the home of the Sopranos, and also the home of AT&T Bell Laboratories, when Ma Bell was Ma Bell. And I had a summer job in the summer of 1968 after my junior year at MIT. Worked on a project motivated by First Lady, Lady Bird Johnson's Beautify America project. And AT&T's idea at this point, this is 45 years ago, was to do away with telephone poles. We were going to have wires going underground. And they had this one wild idea, which was to have a device that had minimal disruption of the surface. Called it the mole. It looked like a torpedo with a pointy end and a hydraulic piston that would allow it to tunnel itself through the subsurface, minimally disrupting the surface and allowing you to pull telephone lines behind it. Now, of course, you needed to control where the mole went, and the ground is actually buoyant, and if left on its own, the mole would slowly surface, probably coming up in the middle of somebody's herb garden. So they designed it with an articulating tail that could, in fact, turn the vehicle or make it go down, depending on how it was oriented, to keep it from having these problems. Now, of course, you needed to know where the mole was to control it. And they had an ingenious idea of laying out wires along the surface where they wanted the mole to go and setting up currents at two different frequencies so that the magnetic fields, when sensed at the mole, assuming that the mole hadn't pounded itself silly, could tell you in principle where it was. Now, I had just taken my first course in classical control at MIT as an undergraduate, and my job was to design the control system for this. And I came up with a design which worked some of the time. Now, you're going to see a number of drawings in this, and I'd like to tell you that I made them all, but there are at least several people in the audience who know that that's not true, so I won't tell you that. Fortunately for me, Mike Rabins, who was then at what was known as Brooklyn Polytech, guided me to look at some of the just recently emerging aspects of modern control theory, controllability gramians, observability gramians, things I had never heard of, let alone worked with. And those helped me two ways. One is it helped me see how difficult controlling this mole was, but in addition, it led to a couple of lessons. And the first lesson was that internships can be remarkably important, not only for the fact that they provide tremendous motivation for the courses you're going to go back and learn, but in addition, to be challenged to work on problems that aren't as nicely packaged as the ones we give on problem sets and exams. The other lesson is a dual of something. There's a well-known phrase, which is there's nothing so practical as a good theory. Well, there's nothing that motivates a new theory more than a good practical application. That was the first time I'd experienced that. That first Bell experience led to my getting a job the next year between my senior year and starting graduate school at MIT. And the projects that I worked on there are less important than the fact that I was extraordinarily lucky to work with a set of people who were working at the cutting edge of mathematical system theory. One of them, Len Forrest, is pictured here. And during that summer, several of them lamented to me that it was too bad that liberal arts college upriver from the world's greatest technological institution had lured away one of the rising stars of control theory. Now, I had a really nice fellowship which gave me great freedom, and I used that freedom when I returned to MIT to take the Red Line up 2 stops and walk across Harvard Yard to meet with Roger Brockett. And that was an extraordinarily important point in my life. So Roger asked me to get involved in one of his projects, and he pointed me to a research problem on optimal estimation on something called Lie groups. What that is not important. What was important to me was this was going to be a fantastic, major breakthrough. It was going to push the envelope of what people understood about estimation extraordinarily far. And I worked on it and got nowhere. And so what I did, I was so discouraged and depressed by this that I took refuge in a place where nobody knows your name and simultaneously you're with thousands of your closest friends, Fenway Park. I went to many games and I scribbled on the corners of programs, and taking a fork, I put Lie groups aside for the moment and turned to the topic of systems on finite groups that Roger had introduced in one of his classes, and obtained the first significant result of my thesis in the bleachers at Fenway Park. And without realizing it, had received a precursor to the next lesson. A few things. First, yes, the Red Sox are acknowledged in my thesis. Second, the work on finite groups actually turned into about half of my doctoral thesis. And a couple of years later, a master's student at Case Western Reserve picked up on this work and took it a good bit farther. So I was very happy to welcome Howard Chiswick as a doctoral student at MIT. The other one involves an MIT regulation. See, if you're teaching a course that has a regularly scheduled final exam, you can hand out a problem set that covers the material in the last week of the semester. And the students can be made responsible for that, but you're not allowed to collect the problem set. So you always had a date issued and a date due, and I'd always put never for the date due, until the agony of the Red Sox defeat in the 1986 World Series. After that, I changed the date due to the next time the Red Sox win the World Series. When that event happened in 2004, I came in the next morning and slipped under my door was a completed problem set with a note on it saying, sorry, it's a few hours late, submitted to me by a then graduate student in my course, Emily Fox, now in the statistics faculty here at UW. I also received an email from a student who's no longer at MIT and had taken my course several years earlier, asking for an extension. When I told Roger about my discouragement with Lie groups, he made a suggestion that shocked and horrified me. He wanted me to work on a simple example. I didn't want a simple example. I wanted a big theory. Well, that example turned into the other half of my thesis, and with that I learned one of the most important lessons in research. It is really easy to formulate hard problems that taken completely head on, you're not going to make any progress on. A lot of the creativity in what we do is figuring out what questions to ask that'll push the envelope of understanding and in fact can be solved. And I resonate with this with the words of two individuals. The first is the Nobel laureate, the late Sir Peter Medawar, who wrote a book on originality and creativity in science called The Art of the Soluble. Now, he meant the art of the solvable, but he was British and didn't speak American. The other individual was Eugene Big Daddy Lipscomb, a ferocious defensive lineman, most notably for the Baltimore Colts of the late 1950s. Big Daddy was asked how he played his position. And what he said was, well, when the ball is hiked, I grab as many players on the other team as I can. And what he would then do is to take those players one by one and toss them aside until he found the one with the ball. That one he didn't toss aside. So when I think about a research area I'm working in my current state of understanding and a place I'd like to get, there usually are many dimensions in which I would have to extend my understanding. So what I mentally imagine doing is taking all those dimensions and throwing them away one by one till there's one left. One thing I don't understand, but on which I think I can make progress. That one I don't toss aside. So I'm deeply indebted to Roger for introducing me to research in the way it's supposed to work. I should also add that Roger was the source of a recurring nightmare when he told me that there was a great theorem-eating God in the sky, and my job was to keep feeding him theorems. That's something that I still have problems at night sometimes. I also want to mention two of the other members of my dissertation committee who were enormously important to me. The first of them is Sanjoy Mitter, who some of you may know, who has the most encyclopedic knowledge of science and engineering of anybody I know, with the possible exception of previous Lytle lecturer Tom Kylath. And Sanjoy is the one who taught me that how crucial scholarship is, both in choosing problems and understanding and putting your work into perspective. And I hope I've been able to impart that to my students. And from both Roger and Wally Vandervelde, I learned the importance of writing. And I don't know about many of you, but when I was a starting research student, I didn't think much about writing. Well, Roger disabused me of that. He pointed me, and this was a decade after it came out, just a decade after it came out, to the first paper that Rudy Kalman wrote on the Kalman filter. Now, if you're not familiar with the Kalman filter was a recipe for taking all of the data from available sensors. So think about a launch of an Apollo mission. So you've got gyroscopes, accelerometers, air data sensors, tracking radars. Taking all of those together with knowledge of the dynamics, the boost phase of the Saturn V, for example, and combining them dynamically together and at every instant in time providing you with the best estimate of the state of the system, position, orientation, and velocity. Now, if you really want to learn about Kalman filters, I would suggest the best place to do that is, in fact, in the textbooks and papers of previous Lytle lecturer Tom Kylath. Now, many of the pieces of the Kalman filter had actually been around for a while, but when you read Kalman's paper, he put it all together. He showed why this was a departure from the methods that had been used before, the Wiener filter in World War II and the approaches right after World War II, and how it was crucial for emerging applications such as in aerospace, and how it redefined what you meant by a solution in terms of emerging technology. The solution was an algorithm that required digital computation. And for all of that, despite the fact that some of these pieces had been around there for a while, Gauss had some of them, Rudy deserves the credit that he got for this. Now, as far as Wally goes, I did not work with Wally, he was on my committee. He read every word of every chapter and challenged me on anything that he found obscure. Now, to help you understand this, Wally is one of the finest teachers that I've ever met. He also has a deep, resonant voice, an extraordinary voice. And so imagine having every chapter of your thesis challenged by someone who is absolutely perfect in immaculate understanding of technical communication, and also might have given James Earl Jones a run for his money for the voice of Darth Vader. So what I planned to do at that point was to use Wally as a target for what I was writing. And what I tell my students is to think of somebody in the field, somebody not intimately familiar with their work, but who they would like to impress with the work. And writing, keeping in mind whether those individuals would understand the value in what the student was doing, and most importantly, would be willing to invest their most dear resource, their time, to read the work thoroughly. As I was finishing my doctorate in 1973, I engaged in a geographically constrained job search. I applied for the faculty position at MIT, but other than that, I applied to very fine research and development organizations and companies in the greater Boston area. One of those was TASC, the Analytic Sciences Corporation, which worked exactly in the sweet spot of what I did, optimal estimation. But the day before I had my interview at TASC, I got the job offer at MIT, which led to a fair amount of celebration and to my arriving at my interview and saying, you know, I'm not going to take a job, but I sure would like a summer job, and maybe you can give me some consulting to do after that. That represented an important event and fork in the road for me. See, TASC had done a lot of work using Kalman filtering, especially on inertial navigation systems, ones that have gyroscopes and accelerometers. And for some of their applications, they looked at the problem of very accurate calibration and alignment of these platforms. And that required measuring continually to get the errors in your estimates down as far as you could. So let's think about a simpler problem. Suppose there's something I want to estimate, measure. We've all heard the expression, measure twice, cut once. Well, maybe I want to measure 1,000,000 times or more. I'm going to get something that's more and more accurate. However, suppose between that millionth and million first measurement, the value of what I measure changes. A sensor fatigues and a bias or a drift develops. How much weight am I going to put on that millionth first measurement when the preponderance of evidence gives me a different value? Well, maybe what I want to do is put more weight on the most recent data. But then I'm going to sacrifice accuracy if there aren't any failures that occur. How can I have my cake and eat it too in much more complicated situations in which I have a number of sensors of very different types, all of which are interrelated through the dynamics of a complex system? And that was the problem that was put before me during my summer job, and it led to my entree into a field that was just about to become hot: failure detection for dynamic systems. So over the next few years, I followed Yogi's advice. I continued working on Lie groups and finite groups. I was also very fortunate to build a consulting relationship with the Draper Laboratories, previously called the Instrumentation Lab. This was the home and the birthplace of inertial navigation. All of the navigation systems for Apollo and the other space programs were, in fact, developed there. And I was very fortunate to get involved in a couple of consulting projects there. One of them was a really interesting one on automatic detection of arrhythmias and electrocardiograms. The other was to look at failure detection for NASA's F-8 digital fly-by-wire aircraft. Again, this was very early on when the idea of a computer controlling the surfaces of an airplane were just being experimentally considered. And what they wanted to do was to develop a system to make sure that this algorithm that was going to control the airplane would not fail because of the fact that it didn't realize that there were problems with the sensors. These projects, both of which were quite successful, were profoundly important for a couple of reasons. One is the statistical methods that underlie the solutions to both of those problems are the same. And that's something that draws any of us who are in the information sciences to this field. It's the fact that the methodologies we develop are so broadly applicable. It's incredible the number of different things that we get to work on, and I'll give you a few examples of that. The F-8 project was particularly meaningful for another reason. What we developed was going to be flight tested, and Draper had stuck its neck out on this. We had to have something that worked. So we needed to be devil's advocate, our own devil's advocate, with every assumption we made in designing this. And the challenge that we had before us, and the game rules of this problem, were to do this with what's called analytical redundancy rather than hardware redundancy. So the ground rule was, we'll assume that these are very reliable sensors. So during a mission, at most one sensor will fail. Well, if you then have 3 identical sensors or more, you can vote. You can compare them. If one miscompares, you toss it out. Well, what happens if you only have 2 identical sensors? Where do you get that other vote? Well, now, the methods that I and others had developed for dynamical systems and failure detection could, in principle, be applied to the entire system and come up with a design. The problem was we knew that different parts of our model had different sources of error. And so what we did instead was to rip the dynamics apart to isolate where we could get analytical redundancy. So a simple example is, suppose I have 2 accelerometers, and they miscompare. I know something might be wrong, but I'm not sure which. Well, I also have a measurement of velocity. So why don't I take a look at the difference in velocity over a time interval and see what each of the accelerometers would predict that difference in velocity to be? And I'd get a 3rd vote. Sounds simple. Well, there are a number of things that can make that go wrong. One of the simplest is the fact that the velocity measurement was out on the tip of the airplane. It measured wind speed, speed with respect to the air mass. While the accelerometers, in essence, after you did some other things that we had to analyze, basically produced acceleration with respect to the ground. And so if you were going through a shear layer where the air mass was accelerating by the airplane, you'd see a change in wind speed that had nothing to do with what the accelerometers were measuring. And you could very easily have declared the failed sensor to be unfailed and the unfailed sensor to be failed. That experience provided 2 important interrelated lessons. First, in practice, you don't have the big daddy luxury. You can't wish away some of those dimensions, whether or not you have a theory for them. You better be able to attack the entire problem because Mother Nature is going to come at you with her A game. The second is that the approach we took to ripping that dynamics apart seemed so systematic that I figured there had to be a theory that underlined this. And that led to 2 dissertations back at MIT. This is one of the first and one of the best examples I've experienced where engineering practice drove theory. And that's something that has been of very great importance to me throughout my career. One of the important events in my professional life occurred when Al Oppenheim approached me early in my career with 2 invitations. The first was to collaborate on the book that we've heard about on signals and systems. And by the way, I'll happily take my royalty on your book at the end of the lecture. The success of that book has been gratifying. The process of writing the book was immensely important to me. We agonized over, and I learned an incredible amount of pedagogy in doing this. There's a wonderful quote. He was referring to problems in physics that you can imagine, but it applies elsewhere. It's a quote attributed to Nobel laureate Richard Feynman, that scientific education is the process of telling smaller and smaller lies. So this is a course in which we were introducing Fourier analysis for the first time, breaking down a signal into its components at different frequencies, and showing the students all of these fantastic things that we could do with these. Did we really need to go through all of the mathematical background that in fact validated what we were doing when we were first trying to get him excited about this topic? It's also the case that the process of writing that book in some sense ruined me, because in doing that, you worry so much about writing everything carefully and concisely that it's difficult for me to do that quickly. And I'm actually reminded of a quote that I use a number of times. It's one that was employed by a number of people, including Pascal, Voltaire, Mark Twain, and John Locke, each of whom wrote a letter to a friend, apologized for writing a long letter because he didn't have time to write a short one. Now, Al's second invitation was to give a plenary lecture on the relationship between what was to become my old field, control and systems, and what was emerging without my realizing it as my new field, signal processing. And during the many discussions with Al, we often talked about the excitement of the hunt, the creative process of trying to figure out what problem you're going to go after and solve. This is with extraordinary apologies to Michael Angelo, and with a great deal of presumption. You can imagine a way of thinking about this. Another way I visualize it is there's an area I'm interested in working in it, and somewhere in it is a problem that I can solve. And my job is to liberate it. And that's one of the important things about research that a lot of people, when they're first getting into it, don't understand, is how creative it is. And it's a thrill to do it. During that time, I also realized that I really enjoyed working across interdisciplinary boundaries. And putting modesty aside, one of my strengths, I think, is the ability to see across those boundaries, elucidate them to others, and bring ideas from one discipline to fruitful use in another discipline. Al also got me involved in a consulting relationship with the research and development part of Schlumberger, which is a company that collects and processes and analyzes data for oil companies. And Alan got me involved with a group that was then headed by Bob Porter when he was at Schlumberger. I know he spent a number of years here as well. And there were two things that happened there that helped me figure out what I wanted to do in signal processing. The first one was a meeting with some really sharp mathematical physicists who were working on these problems. And they showed me traces of data, big pieces of graph paper that went on for almost a kilometer, if you unrolled it. And what these were measuring different things down boreholes, down oil well holes, measuring all sorts of different kind of properties. And what I did when I took a look at this was ask them a question, which was, well, gee, what information are you trying to extract out of these data? And that led to a lot of discussions about what that question means, and it led to my realizing that what I was interested in working on is something that became known as model-based signal processing. So excuse me, I'll bring him back up in a minute. So in this context, I began to realize that the concept of information, as far as I'm concerned, requires models. Without having a model, I don't know how you separate information from noise. And as I'll illustrate later, one person's information might be somebody else's noise. Moreover, while the underlying physics of many of these phenomena can be viewed as absolute, the models of use for signal processing aren't. When I think about the models that are of interest to me, first of all, there's the model for the underlying phenomenon. So in the context of Schlumberger, this might be the different geological processes that led to the depositing of the different layers of the Earth. It was a riverbed with the current running at a certain speed and a certain amount of sinuosity in the river. Maybe it was a sand dune with the prevailing wind at a particular speed, which led to deposits. Or maybe it was volcanic. And each of those, you could have complicated physics describing exactly how the rocks were laid out. So that's the phenomenon. You also have the observables, the things you're going to measure, those traces of data, and how they relate to the things that are in the phenomenon. And there's a third thing. They're the desirables, the things you're trying to infer from the data. So for example, you might want to know where there are layers where you've got impermeable layers with some permeable stuff in the middle, which might be a place where there would be hydrocarbons that you could extract. And usually that's much smaller dimension than the phenomenon. So you've got this picture where the physics plays the middleman. And what I want as a signal processor to use only as much physics as I need to get a good statistically significant model between observables and desirables. To use a phrase that has real technical rather than pejorative meaning, any other aspects of the physics beyond those are a nuisance. So at this time, Al and Bob organized a meeting at Schlumberger, bringing together researchers from a variety of fields. And one of those is a fellow then at Woods Hole Oceanographic Institution, Bob Spindell. So Bob was at Woods Hole, and he talked about topics that absolutely fascinated me. He talked about long-distance ocean measurements, things that he became well known for here at UW. That led to what are called inverse problems with characteristics light, but actually more complicated than tomography, CAT scanning. But he also talked about something else. He talked about the geometry of the ocean, the location and the shape of the Gulf Stream, and things called cold core and warm core rings that spin off of this. These aren't fundamental variables of ocean physics, but they're extraordinarily important macroscopic features. How much of the underlying physics do I need if what I want to focus on is characterizing those? So those encounters helped me in thinking about where I might make a difference, which initially led, in a simpler setting than Bob's, again thinking about Big Daddy, to work on what were at the time unconventional approaches to tomography, focusing explicitly on extracting and exploiting geometry in the scenes we were looking at, with thanks to 3 superb doctoral students. In a few minutes, I'll give you some examples of some more recent work along these lines. And yet another important part of my professional journey involved several individuals, most notably Mike Athens and Nils Sandell. Now, Mike also had a profound effect on my personal life. As director of the MIT lab that I now lead, Mike hired a then aspiring and subsequently very successful children's book illustrator as a temporary employee. That person, Suzanne Natti, is now my wife and my personal illustrator. Nils had been a fellow graduate student, a fellow colleague on the faculty, and most importantly, my catcher on our fast-pitch softball team. He had also always had the itch to form a company, and he and Mike and 2 other friends asked me to join them. And that company, Alphatech, represents a deep and very important part of my professional education and accomplishment. My consulting at Alphatech and elsewhere sharpened my perspective on the difference between what it means to deliver in those venues versus what it means to deliver at MIT or at a university. In the former, the focus is on delivering for the customer. You don't typically have the Big Daddy luxury. The customer is going to need a complete solution to the entire problem, whether or not you have theory to back up every piece of it. That was also extremely helpful to me in my MIT research because I could see where advances in basic theory were dearly needed. And that's how we at research universities deliver. We deliver by developing foundational understanding and by helping to guide the professional development of our greatest asset, the students who work with us. So Alphatech was a place that attracted the best and brightest. And while I would never compare my modest experience with that of previous Lytle lecturer Irwin Jacobs, I did learn a few things about building a company, and especially about ensuring that every one of those best and brightest felt that he or she could move the dial, could influence the direction of the company, and that their work was valued. All of this together with my other consulting experiences not only added to my professional experiences in education, but also complemented and enhanced my academic research in very meaningful and ways that continue today. Another pivotal event came about thanks to my two sabbaticals in France. I came over to Paris in 1980 with several objectives. The first was to complete the problems for signals and systems. And I have to tell you that if you need to make up endless numbers of problems on convolutions, Fourier transforms, filtering, modulation, I strongly recommend doing it while you live in Paris. The other objective was to think about the future research I wanted to do in signal and image processing, and specifically about abrupt change detection. And that took on added focus thanks to two individuals, Albert Benveniste and Michel Basseville. That interaction began in a less than promising manner. The Schlumberger lab outside of Paris hired me as a consultant, primarily to oversee a project they were just starting with Albert and Michel and applying methods of abrupt change detection to some of those signals that I'd seen at Schlumberger. My oversight role added some tension to our initial relationship, and we spent several days telling each other where the other one was wrong. Now, it turns out that we all like to argue, and this turned out to be a lot of fun in our relationship. However, initially, I didn't think this was going to be a pleasant or long-lasting experience. I was incredibly wrong. Our collaboration and friendship flourished both during that sabbatical and after my return to MIT, and the really big event that once again influenced the direction that I took my research came when Albert and Michel came over and proposed that I spend my next sabbatical with them, and that we take a look at this new hot topic that was being proposed as the best thing for everything from signal processing to making world-class Pinot Noir. Could we make statistical signal processing sense out of wavelets? I can honestly say that's the only time I've ever felt like Dustin Hoffman. So I came to Rennes with my family, and Albert Michel and I, together with a student of mine, Ken Chow, wanted to understand the wavelets research of people such as Yves Meyer, Stéphane Malat, and previous Lytle lecturer Ingrid Dobeschi, none of whom spoke about statistical models. What we wanted to discover a framework which wavelets weren't just a good thing to do, they were absolutely the right thing to do. Well, in a sense, that goal was answered a number of years later at MIT by a postdoc from Morocco and France, who inexplicably became a rabid fan of the New England Patriots. That wasn't what we got first from our work. So to give you a picture of this, if you're not familiar with wavelets are a way of analyzing a signal. And they break the signal up into its behavior at different resolutions. So think about temperature variations in Seattle in 2012. You can compute the average temperature in 2012. You can compute the average temperature in each quarter of the year or each season, the average temperature in each month, maybe the average temperature in the morning, maybe the average temperature in the evening. That's breaking the signal down into its pieces at different resolutions. But that's not a model. That's a way of analyzing things. The perspective of starting with models rather than processing, as well as our grounding in dynamic systems, led to our thinking backwards, that is, creating a class of models that synthesize signals from resolution to resolution. And what you're looking over here on the right are two multi-resolution trees, where each level in those represents a level of resolution in whatever phenomenon you're trying to model. And the statistical relationships between them are captured in the model. Okay, these classes of model turned out to be extremely valuable, and they led to extremely powerful algorithms and a variety of successful applications, some of which we followed through on, and many of which were followed through by people in other fields, including some that I can barely pronounce. So one of the wonderful aspects of the field I'm in is that it's provided me with the opportunity to learn about other areas in which I'm by no means an expert, but could work with experts. For example, in oceanography, where my student Paul Figut and I had the privilege of working with one of the world's great oceanographers, Carl Wunsch. Now, some of you may know sea level isn't level. Once you take out the effects of tides and gravity waves, water flows downhill. And understanding those variations in sea level are crucial to understanding ocean circulation. Now, the variation in sea level over the entire planet is on the order of a meter. And so you need to be able to measure that variation to a few centimeters to be able to get the information. How do you do that? Well, one of the things that's up there are a number of satellites. And these are the tracks of something known as the Topex-Poseidon satellite, which has has an altimeter on it, which measures the distance from the satellite to the surface of the ocean. Now, after you take out the effects of tides and other things, you've got a surface, but you still need to know which way is down. Well, down obviously means something different in New Zealand than it does in Great Britain, but it's more complicated than that. Not only is the Earth not a sphere, but the mass is not distributed evenly. What you need is something called the geoid, the equipotential surface of the Earth's gravitational field. And down at every point in that surface is perpendicular inward to that surface. So people have developed geoids. We took one of those. We took our tide-corrected Topex-Poseidon data, subtracted from it the geoid at every point, and had a signal that was a noisy measurement of sea surface anomaly, the variation in sea level at each of the points along the tracks. Now, it's the case that the ocean displays behaviors at a staggering variety of scales. And if you examine the detailed physics of Navier-Stokes, you'll in fact find out that that's the case. But we wanted a much simpler model that was just a multi-resolution model. We wanted to capture the multi-resolution behavior. So we built one on one of those pyramidal graphs that I showed before, and we're able then to come up with lightning-fast algorithms that produce these extraordinarily uninteresting pictures. So the picture in the middle at every point is based on our statistical multi-resolution model and on these noisy measurements along the Topex-Poseidon path. Those are the best estimates based on those models of sea surface anomaly at those points. The picture on the right at each point is a measure of the accuracy you believe you have in that estimate, the variance of that estimate at each of those points. So now you can imagine an experiment, which is let's take a look at any point along that we have a measurement that Topex-Poseidon has. Let's do the tide correction for it, subtract our geoid from it, and look at the difference between that and what the estimate is in the middle picture at that point. If that difference is large compared to what the picture on the right says the variation could be, something's wrong. In fact, that's the basis of most of the abrupt change detection methods that we had developed. And the issue is, what in your model is wrong with that? Could it be the way you've described the statistical variability at multiple scales of ocean height variation? Or could it be the fact that your measurement is noisier than you thought it was? So what we did was we plotted all the places where we had those anomalies, statistically significant differences between the data and our estimate, as little x's on a plot, and this is overlaid on a plot of bathymetry, the topography of the bottom of the ocean. And there are very significant features where in the bottom of the ocean. Deep trenches, large seamounts, volcanic ones in particular, that don't quite reach the surface. And what this suggested very strongly was that we didn't know the geoid very accurately at those points. So we had to reprocess our data in order either to correct the geoid or to, in fact, downweight the importance on those data, or, in fact, to do both. And so that was an important application for us. A point I should make about this is that something that's I find quite interesting is that for some people, the accuracy they want in understanding gravity is relaxed enough that they'll take that tide-corrected Topex-Poseidon measurement and use that as their estimate of the geoid. But it's the difference between that and the geoid that's the oceanographer's entire signal. One person's information can be another person's noise. And it's an important thing that all of us who work in statistical methods often try to capture. And here's another application we got involved in the area of groundwater hydrology. My student Mike Daniel and I worked with an expert in this field, my colleague Dennis McLaughlin. And this was a simulation study aimed at seeing could we solve a problem that people in groundwater hydrology often think about. People in oil companies also think about this problem as well. The two have complementary views. For the people in groundwater hydrology, the good stuff is water, the bad stuff is oil. For the people in the oil industry, the good stuff is oil, the bad stuff is water. But the problems are basically the same. Suppose I've got a source of contamination located in the subsurface somewhere. What we would like to know is how much time it's going to take that contaminant to escape from some specified region that I've specified around this. And for simplicity, what I'm going to do is to assume that we're looking at a particular layer of the earth in which groundwater flows, and the contaminants are in that layer. Assume also at the fundamental quantity that's key to the physics of this is what's known as hydraulic conductivity. It's the ease with which groundwater will flow through the rock at every point in the subsurface. So let's assume we've pixelated this region at a fairly fine scale, so we have a value, an unknown value of this hydraulic conductivity at each point. Now we've got to figure out what measurements we have. Well, you drill a few wells, and you actually measure hydraulic conductivity at a small number of those pixels. That's just a small number of measurements. What else do? You perform pump tests. You pump at one well and see the water draw down in the others. That gives you a much more aggregate picture of hydraulic communication in the region. Well, I'm going to stick that up higher. It's a coarser measure. I'm going to stick that up higher on my tree. Then there's our desirable, which is the travel time that it's going to take to escape a region. That clearly depends on the distribution, hydraulic conductivity in the entire region. I'm going to put that in the top of my tree. Now, that's not yet a model. I still need to do something which is the simpler part to specify the statistical variability in hydraulic conductivity that I believe is there. But now I need to understand how to use some of the physics to relate the observables to the desirables. And what Mike did in his dissertation was, again invoking Big Daddy, look at the simpler case where we could prove principle. So this is the case in which you imagine there's a background conductivity that you know, and the variations on that background conductivity are small. Technically, that meant we could linearize the physics. It allowed us to build a multi-resolution model which produced a picture like this, which most of you are not going to be able to see. So sitting here is a dashed curve. That's obtained lightning fast by processing data up the tree and getting an estimate of escape time from this region. The peak of that distribution, which sits about right here, corresponds as the analog of the value of a sea level height measurement estimate in the middle picture up above. And the dashed curve that shows the spread around that captures the variance, what variability, how much confidence you have in that estimate. So what is the bar chart that sits here? Well, the usual way people do this, which is much more laborious, especially if you're doing it in 3 dimensions, is to take those fine-level hydraulic conductivity measurements, perturb them with amounts that are comparable to the amount of uncertainty you believe that's there. Take all of those values, run it through the complete physics, and see how long it takes a particle to get out. That gives you 1 data point on time. Then do another perturbation and do it again, and do it again, and do it again. And that can take some of the problem that I've seen on this in the days when this computer actually existed and was considered fast. Were usually measured in Cray days in terms of trying to do these computations. We got it in a second doing this. Well, just as he was going out the door and turning to the dark side to go work for Fidelity Investments, Mike took a look at what happens if that assumption of small variations of background were wrong, and you had larger variations. But we still use our model based on the linearized dynamics. As you might expect, it doesn't do nearly as well. So Mike, the dash curve is right here, and the bar curve goes all the way out here. So linearity isn't the right thing to do. But that doesn't defeat the purpose. And while I haven't had another student work on this yet, you can ask, well, gee, are there ways I can learn nonlinear relationships among all of these variables so that, in fact, from those nonlinear relationships, I'll be able to learn a model that faithfully captures this? And there are a variety of methods that one can imagine using for this. The one I would choose to use when we get back to this is a kernel-based method developed by Carlos Gestran, now here in computer science at UW. So while all of this was going on, I was also interested in continuing to work on extracting geometry. An important event came when Tony Yezzi, now at Georgia Tech, came to my group as a postdoc. Now, Tony was an expert in something called curve evolution methods. So what are those? So the idea here is the following. I've got an image, and for every set of curves that I lay down on it, I can compute a reward. And I'll talk about what rewards you might use later. So I can compute a reward. And curve evolution says I've got a set of curves. I want to evolve them till I get the maximum reward. And so that's the nature of curve evolution. You can imagine that at every point on your current curve, you want to decide, is it better to push it out, push it in, or leave it where it is? Although the ways we do this, I'll explain in a minute, are a bit more sophisticated than that. Well, what are the kinds of rewards you can consider? Well, the first place this was used in image processing, people looked at trying to do edge detection, to find the edges of objects, where the assumption was that there was a sharp contrast in intensity between the object and the background. So you give high reward to curves that have high contrast across them. You also give a cost to the length of the curve, because you don't want this curve going up and finding every spurious place of high contrast. So when Tony arrived, all of that was known, but this led to a number of conversations with a number of students, including Andy Tsai here, and to a variety of investigations. Andy, who is now a practicing radiologist, focused his problem on medical image segmentation, in particular problems of importance in image-guided surgery. And another student of mine, Jung-Mo Kim, along with my colleague John Fisher, looked at a problem with a very different notion of reward. And I love this example. So here's an image that Jung-Mo wanted to segment. What he posited was there are objects and there's background. And all I believe is that the distribution of intensities of pixels is different on the objects than it is in the background. I don't know what the distributions are, but I believe they're different. So when you lay down curves, I'm going to give you larger reward if those distributions are more different. You need a measure of what you mean by more different, and my guess is a few of the colleagues here can guess that it was Kovac-Leibler divergence. But there's a measure that you would use on this. And he also put a cost in that had to do with the length of the curve, because he didn't want these things going over, picking out variety of pixels. This example, there are 4 objects. And within those objects, the distribution you get is the one on the right, which has 2 peaks. It's bimodal. The pixels tend to be more black or white, while the background is much more widely spread out over the entire region. It uses all of this. These 2 distributions have the same mean and the same variance. Okay, so Jung-Mo has this cost function that reward function he's going to try to optimize. Now the question, how do you actually do curve evolution? And I find the following analogy useful. Suppose I want to describe the coastline of Hawaii. It might be easier to describe the subsurfaced volcanic mountain range, and the coastline is just where sea level cuts it. Yes, I know the sea isn't level, but this is a metaphor. So you imagine if you do that, as the goddess Pele continues to be angry and grows up that volcano to the southeast of the big island and eventually breaks the surface, you'll get a new piece of coastline. As the atolls to the northwest of the Hawaiian Islands continue to erode and fall below the surface, I'll lose some coastline. And as volcanic islands continue to grow and may merge and to form one island, as 5 volcanoes did to form the big island, I'll end up with another morphology change in the curves, but not in the surfaces. So what you actually do is to evolve a surface and look at where sea level cuts it. So here is the initial what Jung-Mo started with. So what you're seeing here on the top is his initial guess of a curve. So this is a mountain range that's in fact cutting sea level at this wacky set of points. The bottom one says what the distributions of the pixels are inside and outside. They're virtually identical. It's a terrible initial guess. So let's see what his algorithm does. I don't know how it does that. It's pretty good. Now, there are some reasons to think about why this is surprisingly good, but this is actually a very easy problem for anybody who works in the statistical area, and I guess as a few of my colleagues can guess why it's a very easy problem. It's basically an academic parlor trick. That's not all we did, though. We also worked on problems that had real practical significance, and one of those was work done by a former student of mine, Walter's son, who's now at Microsoft Research, was here for a while and left. I think I must have upset him. I think he had some work to do back at MSR. And Walter worked on some problems related to some of the things I talked about earlier. It was oceanography. And one of the problems was to try to map over space and time the temperature variations in the Atlantic Ocean. And there were two issues in particular that we wanted to highlight. One is each satellite pass wouldn't give you a complete image of temperature because typically there are clouds. And where there are clouds, you had obscuration and you had missing data. The other was the Gulf Stream is there. And in fact, there's something called the North Wall, which is roughly speaking the approximate boundary between the warm water of the Gulf Stream and the cold water of the North Atlantic. And so what Walter wanted to do was, in fact, be able to do spatiotemporal smoothing of finding both that North Wall and also the temperature distribution. Now, the Gulf Stream, as many of you probably know, is extraordinarily important. It's actually extraordinarily important to a wide variety of people. It's important to oceanographers, of course. Something you may or may not know is that the total amount of water that flows through the Gulf Stream is more than an order of magnitude larger than the total amount of fresh water that flows into all of the oceans from all of the rivers of the world. It's a pretty big stream. The second people who were interested in it, Bob Spindell was interested in it because the speed of sound depends upon temperature. The Navy's interested in it because that has a significant effect on sonar signals. Fishermen are interested in it because it tells them where there are good places to fish. And meteorologists are interested in it because the warmth of the Gulf Stream can really enhance storms. And the last two came together in a rather tragic way when the Gulf Stream played its role as one part of a triple header that doomed the Andrea Gale and what we locally knew as a no-name storm, but is more popularly known as the perfect storm. So Walter took data that looked like this, and this is a picture showing an overlay of his prediction of the north wall of the Gulf Stream and the data from the next pass, and you can see the white areas where you don't have data. He was able to, in fact, update his estimates of where the Gulf Stream is and produce complete maps of temperature over space and time. Okay. While all of this was going on, I realized that I changed fields again, and machine learning was my home. And a lot of the thanks go to three people who actually said, hey, you're doing machine learning. One was my then MIT colleague, Mike Jordan, and two students then in my group, Martin Wainwright and Eric Sutterth. But something I think is important is what I bring to machine learning is a perspective from my previous home, some things from systems and control and some things from signal processing. And it does reconfirm that I love working across disciplinary boundaries. And here is by far the best and most gratifying lesson. It's our students who continue to amaze and inspire us, and that's where those are the most important others. And here are a number of things I've seen them do in recent years. A stream of superb students developing powerful algorithms and deep understanding for Gaussian graphical models. Now, if you know what Gaussian graphical models are, you'll understand that. If you don't know what Gaussian graphical models are, you won't understand that. So, some very impressive work by two of my students. A best MIT computer science thesis for Jin Choi on the left of building models and discovering hidden variables, where those hidden variables could be interpreted in two different ways. One is they provided context explaining what you saw with the other variables. Jin focused on computer vision, and those variables provided information on what sets of objects tended to appear in the same images. Or you could apply them in places where those hidden variables represented common sources of variability in your observed variables. Jin applied that in a number of places, including to analyzing earnings per share data for the S&P 100. On the right, we have an MIT Best Electrical Engineering thesis for Venkat Chandrasekaran, using a radically different approach to the same problem of uncovering hidden variables. Using methods that build on work of others, most significantly the work of Mariam Fazel here in EE. And an area that Eric Sutterth introduced to us on dynamic Bayesian nonparametric models, including the work of Emily, which won a Best MIT Electrical Engineering Thesis Award and a Best International Applied Statistics Thesis Award. So statistics, electrical engineering, computer science. None of us can figure out what field we're in. And that's something to celebrate. Now, Emily's here, and she can describe the work that she has done in this. If you haven't heard about it, I strongly suggest finding out about it. But I will say a word about the work of a current student, Matt Johnson, and on the application that's here. This is the so-called power disaggregation problem introduced by a colleague of mine about 35 years ago, the late Fred Schweppe. And the problem sounds pretty challenging. I'm going to observe the total power going into a home. And from that one signal, I want you to tell me the pattern of power utilization of every power-consuming device in that house. Lights, refrigerator, washer, dryer. You can do it. Others have showed it, and Matt's work shows dramatically that you can do it. Now, if you read about this, you'll see reasons people think this is useful for various sustainability purposes. But my guess is there are at least a few here who are saying, boy, I don't want that information out there. Isn't it possible to protect it? Well, I'm not working on that problem, but Vince Poor, the previous Lytle lecturer, is. And that brings us to the final lessons. And the first point I want to make is none of the lessons have anything to do with being lucky. Each of us will, during the course of our careers, experience a number of opportunities, any of which could have significant impact on the arc of our career. And so the challenge is to recognize those opportunities, choose among them, and make the most that you choose. So for me, the best lessons are the ones in my title. Listen carefully to others. You never know when you'll receive a kindness that will set you off in a direction you'd never considered before. Be alert to any surprise that arises. You could be in the right place at the right time. And when you come to a fork in the road, at least consider what Yogi Berra had to say. You might want to take it. Thank you.